Good day, students. Welcome to mathgotserved.com. And this clip we're going to be going over how to find the roots or zeros of a polynomial using the fundamental theorem of algebra. Alright, so for the given polynomial equation, we're going to be finding the following. We're going to find the number of complex roots, the number of real roots, imaginary roots, positive real roots, and negative real roots using Descartes' rule of signs. We're going to find the possible rational roots. We're going to factor the polynomial completely and then find what the complex roots are. Alright, so the polynomial equation under consideration for this example is 4x to the to the fifth power minus 4x to the fourth power minus 19x cubed minus 5x squared minus 30x. Okay, let's address the first part. We want to find the number of complex roots. Alright, the complex roots are your rational and irrational and imaginary roots altogether. Okay, number of complex roots. The number of complex roots is basically the degree of the polynomial equation. So you just look for the highest exponent, and that's what it is. So in this polynomial equation, we can clearly see that the highest exponent is power is 5. So the degree of the polynomial is 5. So that automatically tells us that the number of complex roots, which is equal to the degree, is 5. Alright, you cannot have more than 5 complex roots for this polynomial equation. Next, we need to find the possible number of real roots. Can we predict what the possible number of real roots are? Well, you can do that using the number of complex roots. All you do is you take a look at the number of complex roots or the degree, and you look at that or multiples of 2 less. Okay? So the possible number of real roots is the degree or number of complex roots or multiples of 2 less. So you just count down by 2, okay? The reason we count down by 2 is that the irrational roots or imaginary roots occur in conjugate pairs. So you count down by 2 in that fashion, okay? So in this scenario, we already determined that the number of complex roots is 5. So the possible number of real roots is going to be either 5, which is the number of complex roots, or multiples of 2 less. So first multiple of 2 is 2, so 5 minus 2 is 3. We can still subtract 2 from this, so 3 minus 2 is 1, and that's all that there is. So the possible number of real roots is your number of complex roots, which is 5, or multiples of 2 less, or just count down by 2. Okay, 5, 3, and then you subtract another 2, 1. You can't go into the negative realm. It has to be a whole number. Okay, so there goes the answer to the second part. All right, next we want to find the possible number of imaginary roots. Now, if a root is not real, guess what? It's imaginary. Okay, so can we determine what the possible number of imaginary roots are using the information that we have? And the answer is yes. Alright, so since imaginary plus real gives us total number of complex roots, the total number of imaginary roots, possible number of imaginary roots, can be determined by a simple arithmetic computation, which is the number of complex roots minus the what? Number of real roots. Alright, so we just use our two answers from above to determine what they are. So they are going to be, number 1, if you have 5 complex roots, 5 of which are real, so that would be 5 minus 5. If all 5 are real, none are imaginary. Okay? Or you have if you have 5 complex roots, and the other answer we got was 3, right? And 3 of them are imaginary, are real, then that means that 2 have to be imaginary. If you have 5 complex roots again, and 1 of them is real, then that means that the other 4 are going to be imaginary. Okay? So just by subtracting your complex roots, subtracting the possible number of real roots from your complex roots will tell you your possible number of imaginary roots. Okay? So possible number of imaginary roots are simply either none, 2, or 4. Okay? So that's that. Now let's take a look at Descartes' rule of sign in determining the possible number of positive and negative real roots. Okay? All right, let's start with positive. So possible number of positive real roots. All right, so your possible number of positive real roots according to Descartes' rule of sign can be determined by looking for the number of sign changes in f of x. So you figure out the number of sign changes in f of x, or multiples of 2 less, just as we did with the possible number of real roots. Multiples of 2 less. All right, so let's go ahead and look at the number of sign changes that we have for this polynomial equation. So the polynomial equation that we have is 4x to the 5th minus 4x to the 4th minus 19x to the 3rd minus 5x squared minus 30x. All right, let's look at the signs. So first one is positive. This is positive. Any other positive ones? Nope. All the rest terms are negative. So positive, this term is positive. This is negative, 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 negative. Now, how many sign changes are there? We have exactly one sign change. So this one, the first and the second term, it has a sign change. There's a flip there, so there's exactly one. Okay. All right, so let's write that down. We have one sign change. One sign change. So what does that tell us? According to Descartes' rule of signs, the possible number of positive real zeros or real roots is 1. Okay? We can't subtract. If we subtract 2 from 1, we're going to end up with negative. You can't have negative number. Okay, we're counting here. So we have either 0 or anything greater. It has to be a whole number. All right? So the answer is 1 real root for this polynomial equation. This is a prediction that we can make using Descartes' rule of signs. Okay? And then also using Descartes' rule of signs, we can predict the possible number of negative real roots. Okay, so possible number of negative real roots. Now, how do we figure out the possible number of negative real roots? To do this, we are going to look at the number of sign changes of what? Number of sign changes of in f of negative x, or multiples of 2 less. Okay, multiples of 2 less. That's what we're going to do. All right, so let's start off by looking at the original function, polynomial equation. We're going to write it in function form, okay? So let's say the original polynomial equation in function form is 4x to the 5th minus 4x to the 4th minus 19x to the 3rd minus 5x squared minus 30x. This is the related polynomial function. We want to find f of negative x. Okay? So what f of negative x is going to do is you're going to insert negative x for all the x's and simplify. What will happen is that all the terms with a negative power will switch signs, and all the terms with an even powers will remain the same sign. Okay? Just remember that if you take a negative number and you raise it to an odd power, you're going to end up with negative. And if you take a positive number and if you take a negative number um, and you raise it to an even power, your end result sign will be positive. Okay? All right, so let's do the calculations here. So we're going to have 4 times negative x to the fifth minus 4 times negative x to the fourth minus 19 times negative x to the third minus 5 times negative x squared minus 30x. 30 times negative x. Okay? If we simplify using this rule here, we can see that f of negative x is going to be negative 4x to the fifth because of the odd power. This stays the same, negative 4x to the fourth. This one switches to positive 19x to the third. This one stays the same, negative 5x squared. And this one has an odd power of 1, which means that it's going to switch to positive 30x. Okay? So now that we found f of negative x, we're going to use Descartes' rule of sign to look for the number of sign changes. Okay, let's take a look at the positive terms here. The third term is positive. The last term is positive. The rest terms are negative. So we have this is negative, and this is negative. So how many sign changes do you observe here? You notice that the sign flips from the fourth to third term. So this is a sign flip here. That's one. That's a sign flip. And then first, second, third to fourth term, there's another sign flip. Number 2. And then from the fourth to the fifth term, there's another sign flip. Bam. So 3 sign flips. Let's write that down. So we have 3 sign changes in f of negative x. So what does that tell us? Well, it tells us that the possible number of negative real roots are either going to be 3 or multiples of 3. Multiples of 2 less. Okay? So remember, you always just count down by 2. All right? So the possible number of negative real roots is 3 or 3 minus 2, which is 1. All right? So the answer is going to be either 3. We're going to have either 3 negative real roots or exactly 1 negative real root according to Descartes' rule of signs. All right, next we're going to take a look at the possible rational roots that our polynomial equation has. So to find the possible rational roots, we're going to be using the following formula. Okay, so possible rational roots is what we're looking for next. So to find the possible rational roots, we're going to be using the formula. Let's change colors here. It's going to be the positive and negative factors of p, which is the coefficient of last term, or sometimes it's the constant term, okay, or constant. In this problem is going to be the coefficient. Positive and negative factors of p, which is the coefficient of the last term. We'll take that and we're going to divide it by the positive and negative factors of q. Q in this problem is the leading coefficient. Okay? Positive and negative factors of q. Q is known as the leading coefficient. All right, so let's rewrite our polynomial equation. We have 4x to the fifth power minus 4x to the fourth minus 19x to the third minus 5x squared minus 30x. Okay, so in this setup right here, the p term is either the constant, would have a constant, or the coefficient of the last term. So this will be our p term, negative 30. And then our q term will be the leading coefficient. That will be q, which is 4. Alrighty, so we know that p is negative 30 and q is 4. we're good to go. Let's go ahead and find our possible rational roots. So our possible rational roots are going to be the positive and negative factors of p, which is 30, negative 30, sorry, divided by the positive and negative factors of q, which is 4. So positive and negative factors of q, which is 4. Alrighty, so let's go ahead and list the factors of 30. We know what these are. So it's going to be plus or minus 1, plus or minus 2, 3 goes, yes, plus or minus 3, 3 goes into 30 10 times. Does 4 go into 30? Nope. Plus or minus 5 goes into 36 times, 6 goes into 35 times. 6, we're going to go all the way to halfway, okay? 6, 7, 8, 9, 10. Does 10 go? Yes. Plus or minus 10. 11, 12, 13, 14, 15. Plus or minus 15 goes. And then we have plus or minus 30. Okay, so these are the factors of p. We're going to divide that by the positive and negative factors of q. Alrighty, so what are the factors of 4? Plus or minus 1, 1 goes, 2 goes, yes, plus or minus 2, and then plus or minus 4. Alright, so now we're going to list our possible factors. What we're going to do is we're just going to take one factor from the top, and then we're going to pair it with all the factors on the bottom. Okay, and then move on over to the next one. So for example, we'll take positive negative 1 and pair it with 1, 2, 3, and then go to the next one. Positive negative 2 and pair it with 1, 2, 3, and then just keep pairing them up like that. After we're done with all the pairings, then we're going to proceed to simplify it. And in the simplified form, we'll avoid repeating factors that have already been accounted for. Okay, so let's do it. So 1 over 1 plus or minus 1 over 1 plus or minus 1 over 2 plus or minus 1 over 4. That's the first combination using the first factor on the top and the 3 on the bottom. And we have plus or minus 2 over 1 plus or minus 2 over 2 plus or minus 2 over 4. That's the next one. And then plus or minus 3 over 1 plus or minus 3 over 2 plus or minus 3 over 4. That's the next one. And then go to 5 plus or minus 5 over 1 plus or minus 5 over 2 plus or minus 5 over 3. Nope. 5 over 4. And then plus or minus 6 over 1 plus or minus 6 over 2 plus or minus 6 over 4. A few more to go. We have plus or minus now 10, 10 over 1 plus or minus 10 over 2 plus or minus 10 over 4. Next one, plus or minus 15 over 1 plus or minus 15 over 2 plus or minus 15 over 4. Then we have plus or minus 30 over 1 plus or minus 30 over 2, and then plus or minus 30 over 4. Alright, so now what we're going to do is we're going to reduce all of them, okay? And when we reduce, we'll try not to repeat any factors that have already been accounted for. So 1 over 1 is just 1 plus or minus 1, plus or minus 1 half, plus or minus 1 fourth. 2 over 1 is 2, plus or minus 2. 2 over 2 is 1. We already have a 1 here. 2 over 4 is 1 half, already accounted for. Plus or minus 3. Plus or minus 3 over 2. Plus or minus 3 over 4. Plus or minus 5. Plus or minus 5 over 2. Plus or minus 5 over 4. Plus or minus 6. Plus or minus 6 over 3 over 2, which is 3, already accounted for. 6 over 4 reduces to 3 over 2, already accounted for. Plus or minus 10. Plus or minus 10 over 2 is 5, already accounted for. 10 over 4 reduces to 5 over 2, already accounted for. Plus or minus 15 over 1 is plus or minus 15. Plus or minus 15 over 2. Plus or minus 15 over 4. Plus or minus 30. Plus or minus 30 over 2 is 15, already accounted for. Plus or minus 30 over 4 reduced by 2 is 15 over 2, already accounted for. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Plus or minus a total of 32 possible rational roots for this polynomial equation. All right. Okay, so what's the relevance of this? Well, these possible rational roots can help us to achieve the complete factorization of the polynomial equation. So that's the next part. Let's go ahead and find the complete factorization. All right, so the original function, equation is 4x to the fifth power minus 4x to the fourth minus 19x squared, or 19x cubed, minus 5x squared, minus 30x. Okay, so first things first, you can notice that there's a GCF that can be factored out of here, namely x. So you can take out x. You have 5x to the fourth minus 4x to the third minus 19x squared minus 5x minus 30. Okay, so first factorization done. Let's keep on factoring. Now, next thing is to factor this quartic right here. 1, 2, 3, 4, 5 with 5 terms. So factor 4x to the fourth minus 4x to the third minus 19x squared minus 5x minus 30. We're going to factor these by picking possible factors from our list that we got earlier in our possible factors. So there are 32 choices here. So just pick one and hope that it works. Okay? So for the sake of time, we're just going to test the factors that work. All right, because we designed the problem. We're going to test x equals -2. All right, because we know it works. If you're doing this problem, ideally you will just randomly pick whichever one you feel works and you hope it works. If it doesn't, then you go back to another factor. Now, how do you know that a factor works? Well, we're going to show you right now. We're going to use synthetic division to divide it. If we have a remainder of 0, now that means that the test factor we selected is an actual root, okay, or 0 of the polynomial function, related function. So -2. We have put in -2, and then we're using synthetic division, just extract the coefficients. We have 4, -4, -19, -5, and -30. All right, so you know how to do synthetic division. All you do is just add down, multiply across. All right, starting with 0 here, you add down, you have a 4, multiply across, -8, add down, -12, multiply across, 24, add down, +5, multiply across, -10, add down, -15, multiply across, 30, add down, 0. Perfect. So if you have a 0, that means that whatever you selected is a factor, okay? So based on what we have here, x equals -2 is a root. Okay, since the remainder is 0. Since this is a root, it follows that x plus 2, the related factor, is a factor. Okay, x plus 2 is a factor. How did we get x plus 2? Well, if you have x is equal to -2, you just want to set it to 0, right? You just add 2 to both sides, and then you get the related factor, x plus 2 equals 0. All right, so that's how we came up with x plus 2 as a factor. So that gives us a partial factorization. We are going to write down the factors. We have the partial factorization. What do we have? We had an x out earlier, and then we now have another one, x plus 2. And then we're going to use these coefficients right here. These are the coefficients of the depressed polynomial, okay? The polynomial is depressed because it lost this factor, namely x plus 2. So it's 1 degree less than the original because the degree of the factor that was extracted is a degree of 1. All right, so we have 4x to the, see, it was 4x to the fourth before, right? So it's now going to be 4x to the third minus 12x squared plus 5x minus 15. All right, so this is a partial factorization, which indicates that we still have more work to do. So let's go ahead and factor this cubic polynomial expression with 4 terms. Okay, so let's factor 4x to the third minus 12x squared plus 5x minus 15. All right, so we out of this right here we still have 32 choices because we could have a double root. Negative 2 could work again. So ideally, you just randomly pick one to test and hope it works. We're going to pick another one that works because we designed the problem. So we're going to test x equals 3. All right, and then we're going to divide synthetically and show you that it works because our remainder is going to be 0. All right, so set up your synthetic division bars. And then we're testing 3. So you take the coefficients and put them here. 4, negative 12, 5. Make sure no degree term is missing. If a degree term is missing, you have to use a placeholder. Okay? All right, so we're going to add down. 4, multiply across. 4 times 3 is 12. Add down. 0, multiply across. 3 times 0 is 0. Add down, that's 5. Multiply across. 3 times 5 is 15. Add down, you get 0. Bam. That's exactly what we want. So x equals 3 is a root. How do we know x equals 3 is a root? We know it's a root since the remainder is equal to 0. And that tells us that x minus 3 is a factor. Okay? So just set x plus 3. Try to get it equal to 0 by adding 3 to subtracting 3 from both sides. And then you have the factor, which is x minus 3. All right, so that gives us the factorization x times, we had x before, first of all, and then we had x plus 2, and then we have x minus 3. Now take a look at this for a second. This is actually a quadratic binomial. Okay, this is a depressed polynomial. Remember, the power was 3 before. It lost a factor x minus 3. Now it's left with 4x squared plus 5. Now, when you have a quadratic binomial, you want to ask yourself, is it of the special case? If it is of the special case, then it's factorable. If it's not, then it's prime. What is the special case that I speak of? You want to remember the special case a squared. Let's put that over here. A squared minus b squared, right? A difference of squares, or the doses, the difference of squares. If you have a difference of squares, it factors into a plus b times a minus b. If it's not in this format, then it's prime, okay? So if you look at this right here, it's not a difference of squares, so it's not factorable. So this basically tells us that we have achieved complete factorization, ladies and gentlemen. So this is the complete factorization of the polynomial equation. All right, so now with the complete factorization, we can proceed to find out what the complex roots of the polynomial equation are. So to achieve that, we're going to use the zero product property to set every factor to 0. So x equals 0, x plus 2 equals 0, x minus 3 equals 0, and then we solve for x squared plus 5 using the squared property equals 0. This is already solved. This one can be solved by subtracting 2 from both sides. X equals negative 2. Add 3 to both sides here. X equals 3. To solve this, we subtract 5 from both sides. Okay. So that gives us 4x squared equals negative 5. And then divide both sides by 4. And then we are going to get x squared equals negative 5 over 4. And then we take the square root of both sides of the equation. It's a square root. And then you square root that's the top and the bottom. Okay? So remember, anytime you take the square root of a square, you want to insert plus or minus. So x is equal to plus or minus. The square root of negative is I. And then root 5. And then the square root of 4 is 2. Okay? So there goes the last two complex roots. So let's write it down in a set roster notation. The complex roots are as follows. Complex roots are, let's write down the imaginary ones first. Negative I root 5 over 2 and its conjugate. See, they all come in conjugate pairs. The irrational and imaginary roots come in conjugate pairs, okay? So I root 5 is a conjugate pair. And then we have negative 2, 0, and 3. Okay, so there goes your complex roots. All right, so what we would like you to do is take a look at the answer that we got right here, and then take a look at the predictions we made earlier concerning the number of rational roots, the number of imaginary roots, and Descartes' rule of signs. Does our answer agree with what we have earlier? All right, so just post your answers in the comment section below to indicate if our answers agree with the original predictions we made using the Descartes rule of signs and also the fundamental theorem of algebra, and then explain why you think that our answers do agree with it. All right, so this is basically how you find the complex roots of a polynomial equation and other relevant components. Thanks so much for taking the time to watch this presentation. We upload videos to our YouTube page on a daily basis, so don't forget to subscribe to our channel so you can get updates of those uploads. If this presentation helped you in your studies of polynomials, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions or clarifications or special requests for video tutorials, just put it in the comment section below and we'll be more than glad to respond. A bunch of support resources can be found at mathgotserved.com. Do check it out. Thanks again for watching and have a wonderful day. Goodbye.